Okay, welcome to Let's Get to the Marks. We're looking at the A-Level Chemistry Paper 2 Organic and Physical Chemistry exam from 2022. That's Paper 2, A-Level, not AS. And I recommend you press pause before each question, have a go at the question, and then have a go at the walkthrough, which I will go through once you unpause. Awesome. Let's go. So, question one, an acidified solution of butanone reacts with iodine as shown. We've got the equation there. Draw the displayed formula for CH3, CH2, CO, CH2I. Give the name of CH3, CH2, CO, CH2I, and the displayed formula. And it's 2 marks. So we're going to get 1 mark for the displayed formula, 1 mark for the name. So as I said before, pause it, have a go. Here's the answer. First thing we do is circle the CH3 on the structural formula that we've been given here and draw that out in displayed. So, and then we got the CH2 next. So we put C, we display the bonds and the H2. Then we have CO. So you work through the formula piece by piece. That is known as the carbonyl group, the CO group. And then we have CH2 and with an I. And that is your display formula, and that will score you 1 mark. Now we want to work out how to name it. So I could number the carbons like this, 1, 2, 3, 4 from the left, but that would be wrong because we need to number the carbons that give those functional groups of the I and the carbonyl group the lowest possible number. So you do 1, 2, 3, 4 from the other side, from the right. So the name of this is 1-iodo, acknowledging the iodine atom there. Butan, because there's 4 carbons, 2-one, because it's a ketone and the carbonyl group's on the 2. Let's go. 1.2. The rate of the reaction, the weight, the rate equation for the reaction is as follows. We got it here. And then we have been given the initial concentration of CH3, CH2, CO, CH3, I2, and H+. So the question is asking us, calculate the value of the rate constant K. So we want to write out the rate equation, which I'm doing here, except for, I'm using the wrong brackets. I should be using square brackets. So that's a bit dumb of me. And essentially, this question wants us to rearrange this rate equation to find K. So calculate the value for the rate constant K and give the units. And that's worth 3 marks. So what I want to do is divide the concentration of these two reactants underneath rate. So rewrite it out, but move those two to underneath rate. Because they're multiplication on one side, you can divide both sides and move them over. So we now have rate over CH3, CH2, CO, CH3 concentration and the hydrogen ion concentration as well. And that's going to equal K. So I now need to just substitute the numbers from the data in the table into the equation and work out K. And that will score me 2 marks. So 1.45 times 10 to the minus 4, which we're told is the rate, and we're told that over here. And I now need to divide that by the concentration of CH3, CH2, CO, CH3. So I need to put 4.35 in square brackets. You always use square brackets for concentration, which I'm going to multiply by 0.285, and that is the concentration of the hydrogen ions. Notice I put a red X next to I2. It's not in the rate equation, so it doesn't appear in our equation. Okay, it doesn't affect the rate, that reactant. So, and that's going to equal 4.04 times 10 to the minus 5, and that is the value for K. Now, the units for K we need to work out. And we can do that by writing out the units of rate, which are on the top, and that is mol dm minus 3 s minus 1, and putting that over the units for the concentration of the ketone and the hydrogen ions. So both of those have mol dm minus 3. Now, because I've got 2 mol dm minus 3s, I can just cross them out. So essentially, I'm dividing s minus 1 by mol dm minus 3, and that's going to give me mol dm minus 3 S1. So the units are mol dm to the minus 3 S minus 1, and the answer for K is 4.04 times 10 to the minus 5, and that will get you all 3 marks, which is lovely jubbly. Now, the units for K can change depending on the number of concentrations you have at the top and if they're to the power of anything. Okay, let's go. Right, we're on 1.3. Calculate the initial rate of reaction. I've just underlined it here in blue very badly, when all the initial concentrations are halved. So what would happen if we halved CH3, CH2, COCH, and the hydrogen ions, which I've circled here in orange? Well, we can find it out. We just plug the numbers in for the rate equation, and this time you don't need to rearrange it. So it's rate equals K times the concentration of each, and we're halving them, so dividing them by 2, as you can see here. And if I bing, put that in the calculator, we're going to get an answer that is 3.36 times, no, 63, sorry, 3.63 times 10 to the minus 5, and that is what the rate would equal. Check that on your calculator, make sure that is correct. Now, there is an alternative way to do this. We could instead do 1.4. We could write out the initial rate of reaction, which is 1.45 times 10 to the minus 4 mol dm to the minus 3 s minus 1. So 1.45 times 10 to the minus 4. Now, because each of the reactants are first order. Now, if you're wondering what first order means, it means they don't have a little number. Like I've just written 2 oranges there, an orange 2 on each. They don't have that. So they're not to the power of anything. They are first order. And first order have a linear relationship with the rate of reaction, first order reactants. So if I half one, it's going to half the rate of reaction. If I half the other, that will also half the rate of reaction. So I need to divide it by 2 twice, and I'll get the same answer, 3.63 times 10 to the minus 4. So you might prefer that approach. It's a bit quicker. If you spot they're both first order, then they both have the same effect on the rate of reaction. So if you half one, you divide it by 2, half the other, you divide it by 2 again. Right, moving on. Let's go 1.4. Okay, pause the video, have a go at this one. Okay, here's the answer. Basically, when this reaction is finished, what would we observe when all the iodine has reacted? Well, iodine when it's in solution is brown. So when the reaction is done, we should see the color go from brown to colorless. Hope you got that right. Now, let's move on. 1.5. Describe and explain the shape of this graph. We've got rate on the left-hand side, which is represented by 1 over the time, 1 over t. S to the minus 1, and we have temperature along the bottom. Look, as the temperature increases from 20 to 45, what happens to the rate? The rate also increases. 1 over t goes up. So we can just describe that, and that's going to get us a mark. As temperature increases, 1 over t, or we can say as rate increases if we prefer. We can then say, as temperature increases, rate increases, or 1 over t increases. And then the second mark in the describe of this question is that it's not a linear relationship. So if we look at the bottom of the graph, we can see it's less steep. If we look at the top of the graph, it's getting steeper and steeper, the gradient. So the rate, the increase in rate is increasing. And we call this an exponential increase. So it's not a linear relationship, it's exponential. Okay. And now you're going to get 1 mark for explaining why is it that as temperature increases, the rate increases. And simple. More particles have the energy above the activation energy. You can write more particles carry kinetic energy, so more frequent collisions, but I'm not sure that gets you the mark. They're really interested in you saying more particles have energy above the activation energy. And that's the reason for the exponential increase in rate with temperature. And that'll get you 3 marks. 2 for the description, 1 for the explain. Right, deduce the time taken for the reaction at 35. We need to go here to 35 degrees, draw a line up to the line and a line across, and we get 0.03. Now, some students will write that as the time. That's not the time, that's the rate. That's 1 over t. So I need to write 1 over t equals 0.03. For those of you that are bad at maths, you can put this in a magic triangle. So what you can do is you can put anything that's above a divide line at the top of the triangle and the other 2 factors at the bottom. So we've got t times 0.03. And what we're going to do here is go 1 over 0.03 equals time. And if you plop that into your calculator, you'll get 33.3 seconds. So 1 over t equals 0.03. Okay, I feel like I'm talking at 90 miles an hour in my recent videos. For a different reaction, table 2 shows the value of the rate constant at different temperatures. So we've got all the data here for temperature and rate constant for 2 experiments. We've been given this dirty equation, which looks like the Arrhenius equation. And we need to find EA, which is the activation energy. So you've got to rearrange that equation to find EA that's on the right there. So what I'm going to do is first of all simplify by carrying out ln K1 divided by K2. So I want to do 1.55 times 10 to the minus 5, which is K1 in our data table, and divide it by 1.7 times 10 to the minus 14. And if you do that, you're going to get ln 0.0912. Now, I want to get rid of the ln. I basically want to carry that out, and I'm going to get minus 2.39 once you do ln 0.0912 on your scientific calculator. So now I can simplify the equation and write that equals EA over 8.31, which is what R is, multiplied by 1 over T2 minus 1 over T1. So let's simplify it by going 1 over 333 minus 1 over 303. And if we pop that into the calculator and simplify that, we can turn that into one number that's easier to deal with. So let's do 1 over 33 minus 1 over 303. So we're going to get minus 239 equals EA over R, which is 8.31, multiplied by minus 2.97 times 10 to the minus 4. Now, I want to bring that minus 2.97 times 10 to the minus 4 over to the left, and I can do that by dividing both sides by that. So I'm going to end up with minus 2.39 divided by minus 2.97 times 10 to the minus 4, and that is going to equal EA divided by 8.31. Now you should be thinking about, how do I get rid of the 8.31 to leave EA on its own? Well, we're going to multiply both sides by 8.31 because it's being divided. That will get rid of it to leave minus 2.39 divided by minus 2.97 times 10 to the minus 4 multiplied by 8.31, and that will give us the EA. And when we whack that into our calculator, we should come up with the answer of 66. Let me have a little look in the old scientific calculator. Bada bing, bada 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 boom. 66.87 kilojoules. You could round that to 1 dp if you want to. 66.9 kg. All right, hit the like, guys. Let's go. One more bit to do. Okay, 1.8. Name and outline a mechanism for the reaction of butanone with KCN, followed by dilute acids. Okay, so first of all, I'm going to do the mechanism because it's easier to do that than name the mechanism after. So I'm going to draw out butanone. 4 carbons. We need a carbonyl group somewhere on there. So there we go. The carbonyl group has either got to be on the second or third carbon, so it'll always be the second carbon, as it would be an aldehyde if it was on the other ends. Now I've got a nitrile group here with CN, lone pair. Draw the lone pair going to the carbon. Why does it go there? Because I've got delta positive. In AQA, you can just write plus and minus on the carbon and the oxygen here on the carbonyl group. But it's good practice to put a delta sign to mean it's slightly positive or slightly negative. Anyway, my nitrile group, the lone pair is attracted to the carbon. Therefore, the double bond to the oxygen must break because it needs to restore only having 4 bonds around the carbon. That will get you 2 marks for that on the mechanism. Now we're going to draw the intermediate. I'm using the skeletal formula just to show you, you don't have to do displayed, you can do skeletal. So here's my oxygen. Where shall I put the, oh no, I'm going to put the oxygen at the top here. I'm going to flip it around a bit. I'm going to put the lone pair on the oxygen because the double bond broke and went to the oxygen, okay? Now, what's the lone pair going to do? It's going to be attracted to a hydrogen ion. What? You say, where did that hydrogen ion come from? Don't forget, it said we followed the addition of KCM with a dilute acid. Whenever you see hydrogen ions knocking about, an acid's been there. And then I need to draw the bond to the CN. Now what's going to happen, our final product is going to have a hydroxide group, an OH group or hydroxy group attached there, and a nitrile group at the bottom there. So just draw those bonds a little bit straighter on the skeletal. How do we name this? Well, it's called a hydroxynitrile. So you don't need to name it, by the way. That's not one of the marks. You get all 3 marks or all mechanism marks for the mechanism. So we don't need to name this. But if you wanted to name it, you'd count the carbons along 1, 2, 3, 4, and you'd say, it looks to me like 2-hydroxy butan nitrile. Butan 2-nitrile. So 2-hydroxy butan 2-nitrile. Now, what's the name of the mechanism? Well, it's going to be nucleophilic because the nitrile group with the lone pair is a nucleophile. It's attracted to positive things because of its lone pair. And it's going to be nucleophilic addition. How do we know it's addition? We know it's addition because there are 2 reactants, which I'll circle here in blue, and 1 product, which I've circled in orange. So when you have 2 reactants and 1 product, you know it's addition. And nucleophilic because of the nitrile. That's me done.
You're still here? It's over.